This is where we left off in video 2. We had this table filled out, and we had I'm scrolling over here where you can't see. We had this circuit, and we were shorting and opening and filling out the table. Very easy to do. If I go back to our handout that I started with, my next circuit is an AC circuit, and I wanted to show you in Spice the AC circuit part. One thing you notice is I left the 8K alone, but I changed out the power supply for an AC 24 volt. I changed this resistor, which was the 3K, to a 9 microfarad capacitor, and I changed this one, which was a 2K, to a 5.3 millihenry or 5.3 Henry inductor. So if I'm analyzing these by hand, I have to know the frequency. And to know the frequency, usually that's given in a problem. If somebody doesn't give you the frequency, it is considered to be 60 hertz. So we know the frequency. And somewhere over here I've got my results. So I've got a 60 hertz frequency. Because it wasn't given, I need to find the reactance of the components, and that's why I have pulled up Scilab. So I've got a 9 microfarad capacitor. So going into Scilab as my calculator, it's 1 divided by 2 times, and this is how Scilab does pi. It's percent pi, and then it recognizes it as the constant that we're all familiar with, times frequency, which I told you was 60, times my capacitance. Capacitance is 9, micro is 10 to the minus 6. So the way you do scientific notation in Scilab is 9e to the minus 6. So this is 9 times 10 to the minus 6. That's just the syntax it uses. Close parentheses. And I have a capacitive reactance of about 294 ohms. And we call that X. It's actually a subscript C, but when you're typing it out, a capital X and a little c works. Have to do the same thing for the inductor. I have another formula for it, and the inductive reactance is 2 pi times frequency times the inductance. It's not a reciprocal, it's just a straight out multiplication. So it's 2 times, and got to do the pi thing again, times the frequency times my inductance, which is just 5.3. And I have to scroll Scilab up, and I've got about a 1998, so we'll call it a 2000 ohm XL. So I've got about 2000 ohms of XL. Capital X, lowercase l. It's actually a subscript. Now, just like above, I can write equations for this circuit, but we're now in AC, we're now dealing with reactive components. So I'm going to put Scilab where I can get it, hopefully. But which means they are now complex numbers. So if I write my loop equations like I did up here, my IC plus my I8 equals my IL, which is very comparable to this equation right here. So I get IC plus I8 equals IL. So that is the same equation we wrote up here, but now we are in a complex mode, which there's no complex numbers yet, but we'll get there. Okay. When I do the circuit analysis, I'm going to do around the loop again, just like I did last time. So when you're doing AC analysis, even though AC is constantly varying, you take a snapshot of it and write the equations as if it's DC. So there is a moment in time when this is positive with respect to this one, it's negative, and it's worth 24 volts. So at that moment, I'm going to write the equation because it all has to work out. So what you see is my my equation is going to be, and I'll do it like I did last time, IC times X sub C, and X sub C is 294. So my first voltage drop is IC, times 294. Now 294 is a capacitive reactance, and in the complex plane that is a negative Y direction, if you will. Resistance is always in the X direction, horizontal. Reactive components go up and down. So it's not like I did up here, it's not 3000 I3. It's going to wind up being minus 294 I for the imaginary operator times IC. That's my first term. Even though I'm going in the direction of that I think the current's going, even though I'm looping around, the fact that this is a capacitor means I wind up with a negative sign. My next voltage drop will be IL times the inductive reactance, which is right around 2000, and it also is I. So it's a positive 2000 I times IL and then I'm coming around to the voltage source. Well, this is what it was, minus 24 at that moment in time equals 0. Okay, and then I'm going to do the little loop. I'm going to go around this way and back this way, in which case both my terms are going to end up being negative. This one negative due to the capacitance, this one negative due to the fact I think my current runs from left to right, and I'll be looping through that part of the loop from right to left. So if I write that equation, similar to the one up here, I get minus 294 IC minus 8000 I8 equals 0. Now, just like last time, I need a coefficient matrix. My coefficients have changed. I now have IC, IL, and I8 equals COS. Yay. Okay, so now I'm going to pick my terms out. This is a 1. This is a 1. And this is a -1. So one of the things you see is, let's see, IC plus O should be plus I8. And this should be a minus. And a 0. So what you see is our first equation didn't change based on the way we picked current direction in the DC circuit and the way we picked current direction in the AC circuit. Our current directions didn't change. There are no imaginary terms in the current. Our currents will actually come out to be imaginary numbers because they're phase shifted, but in terms of writing the equations, it's not. So I'm going to do the same thing up here that I did there. I've got minus 294I for IC for the second equation. The second equation. And then I've got an IL of 2000I. I don't have an I8 term, and that one's equal 24. So what you see is you see the similarity in the above analysis. And then finally, I'll use my third equation. In this case, they're both negative. So minus 294 minus 294I. I have a 0 term there. Minus 8,000 here. And a 0 term there. Okay. Just like last time, you get your simultaneous equations, you get Scilab to solve it. So just like last time, RR, open parentheses, open brackets, and then my coefficients. The semicolon, none of that's changed. When I go and put in the I operator, everything is multiplied. So minus 294 times, and to tell Scilab I'm using the I operator, it's percent I. So it's percent pi for pi, percent I for I. 2000, and you have to multiply, you have to put in the star 8. Percent I space 0 space 24 semicolon, and then minus 294 times percent I again, space 0 space minus 8,000, this time it has no I, space 0, and here we go. It will let me let me get to where you can see it. Close bracket, close parentheses. So I put in my 3 equations just like I did for the DC part, and there is my currents. Okay, now this is 1.299. D is sometimes used as an exponent to the minus 16th. So we're going to count this as a 0. So this comes out to tell me that my I term, my IC, is this current. Half a milliamp plus 14 milliamps in the I direction. This is my IL current. And this is my I8 current. It's actually negative. Okay. we have to use these complex numbers. And another thing in Scilab is we're looking for voltage drops. So I want to know the voltage across the capacitor and resistor. So the voltage across the capacitor is equal to the voltage across the 8K resistor because they're in parallel. So I can either take the current through the 8K resistor and multiply it times 8,000, or I can take the current through the capacitor and multiply it times its capacitive reactance, which is minus 294I. My choice. How do I do that in Scilab? Well, it's real easy. Scilab is keeping a memory of everything you do. So this is actually an answer matrix. So I'm going to go back and I'm going to up arrow. And I'm going to put in that my AC results equal. Okay, now instead of getting answer, I get AC results, which shows up here in the memory. And now this is in Scilab's memory, so I can use it. So if I want this number here for a current, my IC, I can refer to this variable, row 1, column 4. So my current is AC results, and you gotta spell it right. Open parentheses 1, comma 4, and then I'm gonna multiply that times my capacitive reactance, which is minus 294I. Times a minus 294 times percent I. And that gives me a voltage of 4.12 with an imaginary component. We want the voltage that the voltmeter will actually read, so we don't need the imaginary part, we need the absolute value. So if I just type the absolute value of the answer, it tells me it's about 4.13 volts. So this should come up to be about 4.13 volts. Now, but remember, it has a phase shifter, it has an imaginary component. So I can't simply take 24 volts and subtract 4.13 and get the voltage drop across my inductor. I have to go ahead and multiply it out as well. So my inductor voltage is AC results 24 times my inductance. And I'm a little lazy, so I'm going to up arrow twice and then go in and modify this. Make the 1 a 2, and this 294 is now just 2,000 times I, and then if I hit the enter key, I get my voltage. It's got an imaginary part, and if I absolute value the answer again, I get 28.12. And this is pretty common in AC circuits, particularly if you're mixing capacitors and inductors, that you could actually have a voltages that appear to be greater than your source voltage. So my VL is equal to 28.12. We'll just call it 28. We'll make it 13. That way I'm consistent with my decimals. Okay, so I'm going to save this. And so this is how you would approach AC analysis by hand, just like the DC analysis, but you got those complex numbers, and now you've got a complex matrix to solve. And I don't think the TI-84 can solve a matrix with complex numbers in it, or imaginary numbers in it. And so you have to go to something like a Scilab. If you really want to torture yourself, try it in Excel. I think it'll do it, but some of the commands are just, you'll spend a lot of time in the help desk or in the help files looking to see how to do things. With Scilab, it's pretty straightforward. It's just a handy all-around tool. And this is a good stopping point for this video. Now when I come back for the next video, I will do this same circuit. Let me pull it back up. I'll do this same circuit in LT Spice, and LT Spice will calculate the capacitive reactance, the inductive reactance, and just give us a number. And I think you'll see that, hey, this is really easy. But anyway, thank you for watching.